welcome to the webinar. It's nice to have a good crowd out there as Brooks and Grinfoss conclude our three-part series. We'll be discussing the proper ways of pumping chemicals into a boiler and also its related system componentry. Some preliminary commentary to set the foundation for today's discussion. This program will include a deep dive really into the chemical dosing pumps and systems that are used for injecting chemicals into the boiler and, of course, its associated connected systems and piping. The topic we are discussing is an area really which we've received a number of comments on relating to give us some more information on various dosing systems that are available today because they've changed, and pros and cons for each. Today, to discuss these dosing systems is, as Haley mentioned, we have Jared Gable, and you'll be meeting him shortly after I've had a chance to kind of set this kind of stage, so to speak. So today's agenda, we're going to talk about what a sound water treatment program involves. This is kind of a review of something that we did about a year ago, but I think it's good to highlight that. Then, of course, the mechanical elements that will complement the chemical treatment aspect of a good water treatment program. Keeping the boiler and connected system safe, efficient, and reliable. That's one of the main reasons why we have a sound water treatment program. The major chemical elements, I'm just going to touch on these, some of the things that we will be pumping into the boiler and to the deaerator or the feed system, and, of course, the piping. The chemical dosing systems, this is something that Jared will be covering, the dosing systems and, of course, their applications. Boiler dosing and expert coordination. What he will be stressing here is the importance of the pump manufacturer, the dosing pump manufacturer, and the chemical treatment consultant. There's an understanding between those two in terms of what is going to be used, how it will be dosed, and so on, because that's going to affect the pump, and we'll discuss that. With that, of course, will be the dosing pump details, key points to be aware of, the system options. And it all then really is boiling to the fact that we have a lot to cover today, but it really all begins with the fact that water is a wonderful substance. We depend on it, of course, for our life and in our boiler systems too, but with this fact, we must also be aware of not only its finiteness, its attributes, but we have to be aware of the fact that we can greatly corrode and damage our boiler systems when the water is exposed to the heat that our boiler and our system will provide it. Looking at the typical steam system, you can see the point of greatest heat, of course, the boiler. It's not the only place where impurities precipitate out of the water because of elevating temperatures and thereby corroding or seriously damaging the system. These can all have to be checked and mitigated, or the total system can fail and significant energy can be lost, along with costly production time, possibly some product loss. Starting with the boiler, the place of highest heat release, there are a number of potential problems that we need to contend with in order to protect this very valuable piece of equipment. And you come here. Skin deposition of material on the heat transfer surfaces of the boiler causes significant energy loss and possible vessel failure, which affects the life of the boiler, but costly downtime as well, as I mentioned. And there's the question of how this steam leaving the boiler can affect the process or the piping system due to impurities in the steam or maybe excessive moisture causing serious water hammer and damage to the connected piping. So the minerals and gases which need to be addressed through proper dosing in order to alleviate or mitigate these problems that I mentioned. Of course, the first is hard scale formers, and that's the calcium and magnesium that precipitates out of the water. You can't see it, but it's there. And TDS, the calcium and magnesium that I mentioned before, but also that forms the scale. But then also you have sulfite, which becomes sulfate, causes instability at water level in the boiler itself. You have iron that causes scale. You have silica that deposits, reduces the heat energy transfer rate. You have chlorides that cause instability. And you have alkalinity that causes foaming. And then we have the gases. That would, as you know, oxygen, which causes corrosion, and free carbon dioxide, which also poses the problem. Now, I'm not going to go into a deep discussion of the chemical agents that are used to alleviate or mitigate the possible outcomes listed here. It's to scratch the surface on the most popular chemicals used, along with some general limitations, just to kind of set the stage, because this is a topic for next month when we will talk specifically about various chemical agents in very basic and layman terms. So attending, have a good understanding of the chemistry involved, the what, the why, and the how, but, without getting into the technical weeds, which I think just clouds what really is necessary to understand in order to fully grasp the logic and thereby enhance the due diligence that's required to sustain a solid chemical treatment program. That'll be next month. So in the final analysis, a successful and most economical water treatment program really boils down to two both the mechanical and the chemical solution that will then in tandem and then complement each other. For instance, from a mechanical perspective, we are focusing on the hard scale formers, the calcium and the magnesium. Of course, the consequences that they can cause if they're not properly controlled, well, it is imperative that a water softener be employed to remove these damaging salts. And if a thin softener is used, as is shown here in the picture, the removal of these nasties can be continuous as one tank regenerates while the other tank is in service, and of course rotate back and forth. And continue with mechanical removal of impurities. We see things like sulfate, silica, and alkalinity, which cause all sorts of problems in the boiler, including unstable water line, which is we normally refer to as sink and swell of that water line, in addition to foaming of the boiler water, owing to random boiler outages due to unexpected low water cutoff conditions, and then steam, which ultimately leads to process upsets and possible and dangerous water hammer. Now, these can largely be mitigated by using a dealkalizer. Now, looking similar to a water softener in its appearance, this mechanical removal system uses an anion exchange of salts rather than a cation exchange as is used in the water softener. Now, it's a technical difference, the same result in removing much of these impurities from the boiler's feed water. And then we have a real nasty culprit which attacks the entire system and not just the boiler. That's oxygen. You can hear the damage that it does to carbon steel in a very, very short time if it's done unchecked. And the way at least to start to combat the problem is to employ a means of heating the boiler feed water so as to decrease the oxygen solubility, dry atmosphere, before it can seriously damage the boiler and its connected componentry. Now on this side, you see both a vented receiver on the left with a steam diffusing tube used to heat the water to as close to boiling as possible to give off some of the oxygen. But that is really enough to do the greater part of the job, as the temperature in the tank normally doesn't get much over 180 degrees, leaving much of the free oxygen in the water. For a moderate job of O2 or oxygen removal, one seriously consider a deaerator for removing O2. Under pressure, normally about 5 pounds per square inch gauge, and the equivalent to 227 degrees Fahrenheit, These systems can remove oxygen to almost microscopic proportions, only about 0.005 cc's per liter. Okay, very much of what is involved with the mechanical removal of water impurities. But as I stated earlier, the total job has to be a combination of both mechanical and chemical means. So, expert is to be looking at these impurities as they exist in the boiler feed water and in the boiler after any mechanical remediation. And as you can see, it includes any remaining free oxygen, hardness, silica, and salinity, among other contaminants. But we will be discussing those later, as I mentioned, in future webinars starting next month. For instance, as for limits of oxygen is concerned, many consultants want to limit the oxygen to 0.007 grams per liter in the feed water, while also limiting other contaminants. As far as silica and alkalinity is concerned, here are suggested limits for those when operating at pressures between 0 and 300 psig. 300, by the way, is equivalent to 422 degrees Fahrenheit. And you know, well, that's all well and good about the levels of impurities that can be tolerated in the boiler, but what chemicals are used to limit these impurities, thereby augmenting the mechanical removal devices? The answer is we often encounter a phosphate treatment used to supplement softening, especially when the water is very hard. And this is a treatment strategy which it's been around for a very long time, and though effective, decrease continuous blowdown rates and thereby waste water and energy. Then we threshold scale inhibitor program used for moderate to severe hardness and combines both a phosphonate and a polymer together. Now you'll find that this treatment in applications below 300 pounds operating pressure, so below that 422 degrees. Now as you can see in the visual, this treatment distorts the crystal formation of the calcium and magnesium, not allowing them to bind on the heating surfaces, and thereby allowing the minerals to be removed by surface blowdown. And what they call the solubilizing program, used with using an all-polymer for the chemical agent. And unlike the others, this treatment solubilizes the scale-forming minerals rather than sequestering them. And this actually cuts down on the amount of continuous blowdown required. And as far as the boiler water is concerned, we need to inject sulfite to add on or eliminate any remaining oxygen following preheating and to attack any oxygen which may have entered the boiler due to, let's say, leaks or possibly a vacuum. The sulfite, should be noted here, turns to sulfate, mentioned within the boiler, and which, as you will recall, I should say, is a totally dissolved solid and needs to be removed through continuous blowdown. And speaking of continuous blowdown, I'd be remiss if I didn't mention that in many cases this automatic blowdown results in a continuous stream of very hot boiler water, which needs to be cooled by code before entering the sewer system. Well, we can do that by allowing the effluent to go to a blowdown separator, as shown here with the red arrow on the left, where the hot boiler water is cooled and then dumped to the sewer. But why not reclaim that heated water first by using a blowdown heat recovery system, as shown with the red arrow on the right? Pump cold makeup water through it, absorbing the heat from the effluent before it goes to drain, and send now preheated feed water back to the vented receiver or the aerator. It can make sense to me. Now, I wanted to mention in terms of agents to be dosed into a steam system, are used to prevent corrosion in our condensate return piping. To preventing carbonic acid attack, which you see on the screen now if it's not properly controlled. And they're often attacked. Even the aerator and dealkalizer are employed, which greatly limit the carbon dioxide and the carbonates of alkalinity, cause carbonic acid to form, is through use of chemical amines, as pictured here. And to tell more about how we get the various chemicals I've talked about, just reviewed, in proper places within the boiler and the system, turn the program now over to Jared Gable, Fos Pumps, to talk about that. Jared?
All right. Very much, Steve. Thank you for the setup. Yes, and like Steve mentioned, so I'm going to be talking about the equipment that's used to basically transfer that he ended up speaking about this portion in this of today's webinar. So we're going to look at providing an overview. Make sure I got. Okay, so at providing an overview of the dosing pumps and systems, look at the mechanics of the components, and take a look at some of the more common control panel uses and by good installation practices as to steam boiler systems. So just age a little bit here, our tone. We use HI definition of a metering pump as a forward. Note that it is a reciprocating pump. This means a pump with its moving parts are going back and forth, sort of like a piston in a car, or also these are the word accurately. These are very accurate pumps for good reason, as you will see, and they are very good at handling hazardous and expensive chemicals. So different types of dosing pumps that exist in the market today. Historically, many different solutions and many diverse and complete technologies evolved to become specific problems in steam boilers. Many concepts are available. So on top of the screen is a green pump. It's a hydraulically actuated diaphragm pump. That is with an orange motor that is actually mechanically actuated pump. In the something kind of looking, it's a head pump with common motor. So this is good for multiple injection point, mixing chemicals, or even just increasing the flow rate. And at the top of the screen are some typical solenoid-driven pumps, low flow rates typically, and are very common in the market today. Hand corner is a separate motor-driven pump. More on this pump and this technology later in this webinar. Some types of pumps play a role in the wide variety of dosing pump circumstances that we encounter today in steam boiler systems. So as with typical steam boiler setup and the components, we acknowledge the need for chemical treatment pumps and systems. Injection chemicals can occur at a variety of points in the boiler system, as we will see right here. So in this diagram, you've seen it a couple of times, but here's another look at it with injection points. So the first up at the top left, we see the amine injection in the steam line. Exit boiler is in the upper left-hand corner. In this line will typically range from perhaps 1 to 300 psi. Later, we will discuss how pressure will impact pump selection. You'll see the sulfide injection into the deaerator tank. Mechanical pump rated for lower pressure, since the deaerator tank will normally impart up to 10 psi of back pressure on the pump. This look can be a product in these systems, since dosing pumps require some minimum level of back pressure in order to properly and to dose accuracy. Is that metering pumps will require something like 25 psi. So what we usually see is a back pressure valve set level, and those things are actually absolutely necessary. Otherwise, the pump cannot dose accurately. Benefits of water treatment will be reduced through the treatment of that expensive system. So we got balancing that there. Typically injected between feed pump and the boiler, like Steve mentioned earlier, could be polymers or even the phosphate. All chemicals that we are discussing here are used in a wide variety of forms and concentrations, and these will impact the choice of pump materials and instructions. I'll talk more on this a little bit and a little later. And interesting is the injection of amines into the steam line. So I learned a little bit by through our discussions here, setting this presentation webinar up. Steve, typically chemicals are injected into a liquid process line, and in boiler systems, the injection of amines is an exception. The reason getting into the steam line is to ensure good volatilization of the amine solution and to minimize potential losses that occur by injecting into the DA tank or boiler directly. In the image to the left, you see the fundamental reason for injecting an injection nozzle or quill. So this is the part of the injection valve that is actually inserted into the pipe. Basically, tee in an injection point because liquid will want to follow a path along the pipe wall, and so it doesn't get mixed. It introduced the chemical to the center of the process pipe being treated. For example, if you have that is 4 inches in diameter, you would need a 2-inch injection nozzle or quill. So a stainless injection nozzle. Stainless is a popular choice for the amine injection into the steam line of a boiler system due to its high tolerance for pressure and temperature, so something up to 1,000 psi and even 500 degrees Fahrenheit. Since the of liquid properties can be encountered when injecting, there are strategies for dealing with all these properties. In general, the liquid characteristics that must be considered when selecting a dosing pump for applications. Part of a chemical feed system, the metering pump. All of these have 4 basic components, and they are motor, which can be constant speed, variable speed, or even a solenoid. And then the assembly, which converts the rotary motion into receiving motion, or solenoid is used. And the liquid end. The liquid end is where the liquid comes through. Inside of this are the moving parts that do the actual pumping, so it's the diaphragm, which we'll see in a second. Finally, we have the control adjustment, which is adjustable by varying the stroke length, the stroke frequency, or the motor speed. One common of these types of pumps is that both use diaphragm for pumping the liquid, as I explained a second ago. Note the black diaphragm on the right has a screw to mechanically connected to the reciprocating drive shaft. The one on the left has no mechanical connection to the shaft, but instead pushing up hydraulic fluid to move the diaphragm forward while relying on atmospheric pressure to move the diaphragm back during a suction stroke. They're both robust pumps and good for high pressure applications, while mechanically actuated pumps yield for lower pressure applications and can achieve some lift where there's lifted above the chemical tank liquid level. For selecting dosing pumps in the boiler system are: 1, how high is the pressure line we're injecting into? And 2, the liquid source located above the pump or below it so that there's a suction lift, meaning bringing liquid from the tank lift up to the dosing head of the pump. Are generally speaking good for up to around 300 psi. But this is widely. If, for instance, the pump must be made of composite material such as PVC or Kynar, or it could be stainless steel. The metal is generally good for higher pressures, while the composite ones may be for around 150 psi or so. no general ranges with many exceptions. This is critical to hold discussions on these topics between the company, the chemical supplier, and pump manufacturer. This is something Steve also alluded to in his presentation. We don't have time today, but there are courses available that will demystify the inner workings of both the mechanical and the hydraulic pumps. Okay. So types that are available for dosing pumps. So this is we talked about the spinning into a reciprocating motion. Well, there are conventional motors, stem motors, and solenoids that we can use to do that. A conventional motor, like an AC synchronous motor, can be found on most pumps, fans, and other rotating equipment. And metering they are used to suit different pump designs. For example, the hydraulic pump we just discussed is a conventional motor. The solenoid driver is essentially two magnets that attract and repel each other, power is applied and removed. Because along a shaft, this causes the reciprocating motion by the diaphragm. Pumps with significantly less expensive limitations on performance at the low range. Now, steppers are an advanced type of motor that is a brushless DC motor, but with power input. These complete control over the suction and discharge strokes independently and extremely accurate tire turn-down range of the pump. All driver types are applicable in steam boiler systems. Selection is dependent on a wide variety of factors, including the pump size, metricity, cost, and others. In order to treat water for the boiler system, we need to control the flow rate. So next, let's take a look at how we set those feed rate or dose rates of the metering pump. Now, reciprocating positive displacement devices, so with each stroke, they move a very specific amount of fluid. And control the pump feed rate with a combination of stroke frequency, strength, and motor speed adjustment. Stroke frequency increases, we are drawing in and pushing out more chemical over time, in strokes per minute. The stroke, the more volume displacing each time, and so we realize an increase in feed rate. Motors with a VFD, or in the case of a stepper motor, directly affect strokes per minute also. So for motor-driven pumps, maximum stroke length can be described as 100%, and the maximum frequency of reciprocation also be characterized as 100%. If you have 50% stroke length and 50% stroke frequency, then the total dose rate is figured by multiplying two percentages. So for this example, 50% times 50% equals now 25% of the maximum flow rate. These two factors, or any combination of the two, leave a seemingly endless variety of outputs. There are limitations, but that's getting so deep into the topic that we won't have time to cover today. So another opportunity to learn awaits for us. So with this motor, it's a bit easier because we're simply setting the pump to a desired feed rate. Let's say gallons per hour. So simply going to the pump, telling gallons per hour you want, then that's all the setup there is. These pumps will use 100% stroke length, and so this variable remains constant. Motor is infinitely variable within the minimum and maximum allowable flow limits for each pump. This will make small rotations or steps the course of one revolution. Movement can occur in various intervals and at various speeds of movement. For example, it can have different speeds for the suction stroke than for the discharge stroke. Of these and movement characteristics provide the ability to precisely control the amount of liquid injected and of time which it is injected also. It provides and reliable flow. There's a number of different methods for adjusting the dosing rate and the technology built into the different styles of pumps. we think of the two main selection criteria of any pump, we talk about pressure and flow. It is an exciting view of the dosing pump performance chart, kind of sarcastically because it's just a square. So the pump can operate on lines and anywhere below and to the left of them. So this is significantly different from the centrifugal pump curves that were on the previous webinars that we had with Glenn Foss. When we talk about the meter pumps, the curve or chart is not as important as the maximum and minimum limits. So the maximum flow, the minimum flow, the maximum pressure, things like that. So we don't ask to see curves, but instead we look at tables that show max and minimum performance. We did at a turn down a little bit ago. Now, on the performance chart, is a very important concept with pumps. Technically, quote, a state of relationship between the maximum flow indicated on the pump's chart and the minimum flow that the same unit can dose with accuracy. In other words, is an indication of maximum allowable reduction in flow rate performance while remaining accurate. All right, so let's put this into perspective. One of the amazing things to me about controlled volume dosing pumps is the high accuracy that is coming with a very wide range of flows. These pumps are very accurate down to the values you see here. That are a little familiar with us, that range from 1/100th of a teaspoon per minute to about 150 gallons per minute. That drops from the size of a BB to 2 or 3 of the hot water tanks most of us have in our homes. This range can be achieved by one pump in mind in particular, but you see dosing pumps have a large range in the broad family. What this means today is that a wide variety of flows can be dosed with accuracy across a wide range of sizes of steam boilers. So when a system designer is determining the appropriate flow rate of the metering pump, he or she works through a series of calculations based on the water or process steam flow rate, the chemicals that we will use for treating, and the resulting desired concentration level of the chemical in the treated liquid. These are really beyond the scope of today's webinar. Typically, the treatment company will advise based on the needs of the boiler system. I think that's we'll get into more maybe on next month's session for that. Note on the liquids and choices of pump materials. This seems to be something that comes up often in discussions. Manufacturers publish charts that list a variety of liquid and materials that might be considered for use with each. In the zone here, we can see that amines, steel, and PTFE or Teflon are two of the best choices for material selection, while materials such as PVC and Viton show severe effects, and then to Cole Parmer's online chemical compatibility database, and my personal favorite. These sources, whether printed or found online, are offered as guides, but the final decision on materials of construction must be based on discussions with the contractor and the chemical supplier, since the boiler manufacturer and pump manufacturer cannot be aware of all possible chemistries that exist out there today. Now, don't read the small font of this chart. We're going to have it available to you as a handout at the conclusion of this webinar. This gives you a better idea of all the questions that should be asked and answered while selecting a dosing pump. Note that relationships are established between treatment contractor and chemical supplier and pump manufacturer. Many or even most of these questions can be answered ahead of time. So keep that. Look a little bit more now at the systems approach. It takes more than the dosing pump alone to make a complete dosing system. They consist of a dosing pump simply mounted on top of a 55-gallon drum of chemical. The two benefits of this method are low initial cost and the fact that they require a highly trained technician since they're really easy to operate. But there are package dosing systems that present an easy plug-and-play solution as well and incorporate all the necessary components. Skidded packages have a single source manufacturer typically providing a single point of contact for support. A package dosing system is to piece a system together. This means sourcing components, constraining, and testing all separately, different suppliers. It's more of a larger project for that. So project dosing systems be considered. They're skidded or a tank system. The dosing systems come in integrations and allow all components to function properly together as an integrated system. Second, it is best to install a system with 2 or more pumps for duty standby operation. Allow treatment to continue when pump maintenance is necessary, and the system allows this to be done easily. Inducts have various chemical treating systems employed for various needs, including processed water, sewer discharge cooling waters, and treating boilers, steam systems. We have some of these cases, the systems are monitored at times, even controlled by building or process management systems. Integrated management systems and PLCs is practice when considering chemical feed equipment. Systems are typically constructed necessary control panels that allow system integrators to remotely control chemical feed processes and even gain valuable system feedback. We know that chemicals make up the majority of the operational costs when it comes to these chemical feed systems. It seems like that sometimes can be debatable, but over time, that's where the real cost comes in. So package dosing systems are built around metering pumps that are designed to work most efficiently in ideal system conditions. So let's go to some components now. Because we know that all dosing systems accomplish the same goal, there are some components that are typical in almost all dosing systems. This is an extensive list of possible components. Those inside square are what typically find in a package dosing system. Now, all to dosing and protect the system. So a little bit about each component briefly. First, there's some piping. Colors include PVC, CVC, PVDF, and stainless steel. There are several advantages of selecting one material over the other for a particular application. From chemical resistance to the material's ability to withstand high temperatures and even cost. So now, number 8 on this chart is a white strainer. A white strainer. It is a sort of pre-filter that does not allow debris to pass into the dosing pump head. Think of a pre-treatment for the dosing system. Note here is to always ensure that the screen material in the strainer is also compatible with the pump liquid, not just the white strainer body. So we don't want particles of stainless steel to be sent through into the pump and rip up the diaphragm. And that's the reason. Calibration column. The columns are used to conduct accurate calibration of the metering pumps. Without calibration of the injection, it is first impossible to dose with accuracy. At initial startup and after maintenance, it is good practice to calibrate the metering pumps against actual system pressure. For this reason, most dosing systems come with an integrated calibration cylinder that is appropriately sized for the pumps. It's common calibration or drawdown for 20 to 30 seconds. Number 2, valve. Pressure not specifically for pump protection, but more for the system piping protection. If a downstream is accidentally closed, a relief valve will allow the flow back to the suction side of the pump, or it can be just directed directly to the chemical feed tank. An isolation valve between the pump discharge and the pressure release valve to ensure a clear path to the pumped liquid in a blockage situation. These are, after all, positive displacement pumps we are working with, so something will have to give, and that's when we have that pressure relief valve system. This is the back pressure valve, or sometimes called a pressure loading valve, used in instances where the process pressure is lower than desired for pumps to dose accurately. Now, the pumps that use valves with check valves typically require 25 psi to see check valve. We need a manufacturer for guidance on how to set the back pressure valve to avoid either an overpressure or underpressure situation. In instances, process pressure will fluctuate, so it is not a reliable method to use process pressure or pressure losses in piping to see the check valve due to the varying velocities and pressures that we see in these systems. Pulsation dampener. Pulsation dampeners are generally installed in dosing systems to ensure smooth, continuous flow and reduce vibrations and stress to system by diaphragm metering pumps. All pumps compression and discharge stroke. Their pressure generated by the acceleration and deceleration of pump fluid, and what may cause the piping to actually shake loose at fittings, possibility even break. Pumps with improved drive technology, such as those stepper motors we talked about, are designed to generate a slow discharge stroke and a quick stroke, allowing smooth, continuous dosing and need of a pulsation dampener. So, check pump manufacturer to see pulsation dampener is actually required for the pump being installed on a system. And you can end up seeing some costs on a pulsation dampener that way. There are many other components that make up a complete and fully functional injection system. And these are to assure continued system dosing accurately over time. There's nothing with men on top of a drum, the pump of drum, but it is important to know the other components that will make the treatment more effective in a boiler system. A stainless steel example we saw earlier for the amine. Injectables are part of the complete installation, but are typically outside the scope of a package dosing system. And this is because injections are located at the exact point where the chemical meets the process. Typically, tubing or pipe is used to transport chemical from the discharge of a dosing system to the nozzle. They vary from application to application, and this is why we leave it out of the scope of a package dosing system. We don't know that link. Different types of injection nozzles shown here. Some are a piece of pipe or quill, as we mentioned earlier, and others include check valves with strings or have ball valves and restrictor chains to allow for maintenance in a clean-in-place type of environment. The same basic purpose to evenly disperse chemical in a pipe. If you missed this component, here it is into the relevant boiler piping section or tank. Earlier, we taught integration with building management systems. It was really brief, and with these. The box or hand-off auto panels are typically used in steamboiler systems where the specifications are more stringent and an increased level of automation is desired. Setting pumps to communicate with the building management systems and PLCs by laying control input cables and output cables, input to the pump and output from the pump on a terminal strip, and offer safety like lockout, emergency stop, and some status lights. Alternatively, though, an integrator may decide that there is only a need to apply power to the pumps. Control inputs and outputs can run direct to a PLC, their PLC equipment. Control panels are typically installed directly on a skidded dosing system for convenience. Okay, before I wrap up this part of the webinar, I want to take a look at a few good installation practices and some that are to be avoided. These practices will help to assure an optimally performing boiler water treatment program. The check mark next is an ideal installation. Have a straight line of pipe or tubing with a valve, which is basically a check valve, of the suction line. This maintains prime. To prevent cavitation problems, keep your lines as short and straight as possible. The liquid suction side more than recommended by the pump manufacturer. And please do not create peaks and valleys in your suction line. This will cause all sorts of headaches, permission to start up, things like that. So I've heard that times, and most of the time that it was the poor practices. So keep that in mind. Otherwise, you get the gas or vapor lock, and it's tough to actually move the liquid. So things to be aware of. And use a suction line rather than a flexible one in your chemical tank if a mixer is installed. The suction line does not get tangled with that mixing blade. And it kind of sounds common sense once you read it. But yeah, the flexible suction line can get sucked to vortex and then wrapped up across that shaft. So the rigid line also some clearance from that foot valve to the tank to avoid sucking in sediments that made their way to the bottom of that chemical tank or other, which could cause the valve then later on in the dosing pump to maybe get blocked, which would cause your pump to stop moving fluid. So the handy tip installation. The Grundfos Technical Institute website is a virtual classroom with over 40 self-paced courses to automatically track your progress. The site also has all of Grundfos's webinars, both live and pre-recorded, with more information on the topics that we discussed today for dosing pumps and systems. There is a course there that includes all of the upcoming training events, including face-to-face courses. Completed courses come with a certificate of completion with PH hours, and many of the units come with the CEU credit approval also. Okay, that concludes my portion of the training. I'd like to thank you all for your time, and I'll go ahead and turn it back over.
Very much. Let me just give everyone at least what Jared and I thought before this all started today. What would be the good takeaways? Proper treatment is a combination of mechanical and chemical remediation, as I took you through. Chemical treatment has a significant impact on efficiency, reliability attainment within that total system. In cycles of concentration saves fuel dollars. That means the more that you can concentrate those impurities in the boiler feed water, you have to blow it down. That would be continuous blowdown. Heat from continuous blowdown or TDS control can be recouped. Proper and reliable chemical dosing is paramount for assuring steam boiler system reliability and life. A chemical metering pump is a reciprocating pump used to accurately dispense a specific volume of liquid in a specific amount of time. A meter is in the steam line to assure proper volatilization and dispensing throughout the piping system, especially the condensate line or lines. Have a motor, a drive assembly, liquid end, and a control adjustment. The properties in the chemical to be dispensed need to be evaluated for proper pump type selection and materials of construction. Pneumatically actuated pumps are used for steam boiler applications because they have adequate pressure tolerance and provide the suction lift often required. And when using a chemical dosing pump, what is important is the maximum and minimum pumping limits. And pack dosing systems offer a high degree of assurance that chemicals are being properly dispensed while including ongoing monitoring and alarms. Remember, these chemicals are very, very expensive, so you don't want to overdose. That can cause other problems. So properly pumping and metering the chemicals is extremely important in the overall reliability and effectiveness and efficiency of the total system. So with that, hopefully texting some questions into Haley that she can read to us, and Jared and I will take the next few minutes that we have to try to address those. So let's go ahead, Haley.
All right. So let's go to our first question here. Soap application is up to 300 psig saturated. What about higher pressure or temperatures such as 500 psig with superheat to 750 Fahrenheit?
Jared?
This is for the injection pumps, I'm assuming?
Mm-hmm.
Okay. There are pumps out there that can handle higher temperatures, and also like the hydraulic pumps that can handle up to even like 2,900 psig. So we do